let's Boltzmann Q&A. What is the difference between non-orthogonal, weighted orthogonal, and weighted orthogonal moments? So, of course, this question is important for lattice Boltzmann methods with multiple relaxation times. And it is a question that I would say 99% of everybody who believes they are at the leading edge of lattice Boltzmann modeling in the world do not understand this question. Okay, so this is not a reason that you should not understand it. First of all, coming back to the moments, so we have, of course, a lattice. We have a lattice momentum distribution function in populations, and from this we can derive moments in the countable form that is written up here with summing the distributions over the indices I and j by powers a and b, and so we come to countable moments. And if you don't like countable moments, you can also define a kernel function psi or phi ij and do the multiplication over the distribution function or the populations of the distribution functions and come to a general definition of the moments. And this is, of course, what was done in the original multiple relaxation time lattice Boltzmann methods. And this, first of all, leads us to say countable moments, not countable moments, physical moments. So if you don't like to indicate your moments just by numbers, you can indicate them by their physical meaning. And this has been done for the original lattice Boltzmann methods with the mass, momentum, J, Jx and Jy, and then energy, squared energy, epsilon, heat flux in X, heat flux in Y, momentum flux, and two cases of momentum flux. Okay, so these are the original moments of the multiple relaxation time method, but these moments are not actually used. This is why they have a head, because they are not yet orthogonal. And by orthogonality, we mean that the kernels that are written here, when we multiply the kernels by each other and sum over all the directions, if this sums to 0, this would be considered orthogonal. And what we see here is that the moment E and the moment epsilon, they do not fulfill this condition, and so they are not orthogonal. Okay, so then what was actually used in the original lattice Boltzmann method with multiple relaxation times by Lallemont and Liu is orthogonal moments, where we modify the definition of these kernels in such a way that now the new E and epsilon here will become, if we multiply their kernels and add and sum them over all lattice directions, they will turn out together to be 0, and so these moments will be orthogonal to each other. So now you would probably ask the question, why is this important? And the answer is, we don't know. Yeah. So say somebody is a specialist in lattice Boltzmann, he tells you, do the math, yeah, make them orthogonal, and then everything will be nice. And why? Just believe me, because I'm the god of lattice Boltzmann. Okay. Turns out that this is not the only option to make these moments orthogonal. There is another way to make moments orthogonal, and this is by considering their the lattice weights. So remember that in global equilibrium, not all of the lattice directions come with the same weight, but they have different weights, and these are the weights that are also used in the BGK method. So for example, the ones that go into the diagonal, they have a weight of 1 over 36. The one that go in the cardinal direction, they have a weight of 1 over 9, and the one that is resting has a weight of 4 over 9. And the orthogonalization by Lallement and Liu just ignored that different directions have different weights. So weighted orthogonalization takes this into account by multiplying the kernel under the sum with the weight of the respective direction, and we define that the weighted orthogonality if this sums to 0, which is of course different from the non-weighted orthogonality. So when we do this, we can derive now Ra weighted orthogonal moments, which have a little bit a different definition. That looks now like this. You see these equations here are now turning out to be completely different from the definitions of the unweighted orthogonal moments. So again, what is this good for? Where we do not have a very good explanation why we would do this in 2 dimensions, but I can give you at least a rough idea why this may make sense anyway. So what we actually want to do, or what is the hope, that we can make these different moments independent of each other. So we want to have them as independent variables. And in order for them to be independent of each other, they should also be independent in equilibrium. And now let's have a look whether this is the case. And I just look at one example actually, namely the heat flux Qx, which is a third order moment, whether this is independent of the momentum Jx. And we see if we use non-orthogonal moments, then the momentum here would be rho u, and the equilibrium for this moment Qx would be 1/3 rho u. So we see these two things are just proportional to each other, so they are not independent of each other. Now we would like to see, by the way, I've recognized that I've forgotten here that that this would also have a uv square rho term. That term here would actually be independent because it's a different monomial than the u in terms. So u is the velocity in x direction and v is the velocity in y direction. So if you look at also weighted orthogonality, what we observe is that, of course, the momentum will stay the same, and now we get a scaled Qx, and this scaled Qx, this is now not independent of u. Yeah, so here back here, this is different monomial, u times v square, so this is okay. But here, it is strangely enough, previously we had u here, and now we have minus u here. So we were actually not successful in making it independent of u. We just put u in the other direction. So when instead we use weighted orthogonality, what we get is that this third moment here will become, in fact, independent of u itself. It's still dependent on u times V square, but this is an this of course is an orthogonal, a different monomial, so it is okay to still be dependent on this because this is of course separated by some scale. So unfortunately, this is still not a very good explanation why we use why we need weighted orthogonality, and in fact in 2 dimensions there is no good reason for this at all. The real difference can only be observed in 3 dimensions, and there actually only in the D3Q27 lattice. And actually this is the reason why this lattice was never used for the original MRT methods, multiple relaxation time methods, because this doesn't work with unweighted orthogonality, as it turns out. So the problem here that emerges in 3 dimensions, and I only give a rough sketch of this because it's kind of complicated, is that then we have this moment of forced order. In countable terms, it would be M211. And this guy must relax independently of the moment M011. So the problem here that originates if you try to separate these 2 moments and relax them with different relaxation rates, that if you calculate the equilibrium of these guys by means of factorization, then their equilibrium of M211 should be the product of M200 multiplied by M011, and this normalized by M000. And at the same time, there's a Maxwell equilibrium, and this Maxwell equilibrium, because it's not an odd order moment, but it has odd coefficients, and because it has odd coefficients, it's unsymmetric, and so its equilibrium in the Maxwell sense would be 0. However, according to the factorization, because the moment M200 would be 1/3 rho in equilibrium, we get a different equilibrium here, namely that M211 would be 1/3 M011. And this is the reason why these 2 moments cannot be made relax with different relaxation rates unless we make them weighted orthogonal. So actually this is a pretty complicated thing which I tried to explain, say, the last 14 or so years. So if this is not completely clear to you, then please look into the paper of the cumulant paper that was also linked in the description. And actually you cannot solve this problem properly with moments at all. What you have to do is you have to go to cumulants, and this is something we will learn later. Thank you for listening.